going to start now. Okay. So I'm Myrna Wooders, president of APET. It's my great pleasure to welcome you to this keynote lecture by Eric Maskin, Nobel Laureate from Harvard University. What else should I say? I don't have much to say because all I'm doing is the introductions of people, and Carlos da Costa will tell you a bit more about Eric's work. Okay.
Well, it's a great pleasure to have Professor Maskin here with us. As I think we all know, he is the recipient of the 2007 Nobel Prize in Economics, along with his classmate Roger Myerson and with Leonid Hurwitz, for having laid the foundation of mechanism design theory. That's what's written in the Nobel Prize page. As we all know, like mechanism design, what it does is like to provide an analytical framework for us to understand institutions or to study institutions. And this is not a small thing. When you think about the 1970s as this revolutionary time in terms of economic theory, the first thing that comes to our minds is probably the rational expectation revolution by Bob Lucas and other people. But there was another quieter, maybe, revolution, but not for sure smaller revolution going on in economics. And this has to do with the beginning of mechanism design theory with the work of Leonid Hurwitz. In 1972, he wrote a paper that established the concept of incentive compatibility. And lucky for all of us in the profession, a young student, a young math major at Harvard College, took as he said, by accident, a class by Kenneth Arrow on economics of information, where basically what he did was to show the work of Leonid Hurwitz. He went on to work on mechanism design theory, and a couple of years later, the second important idea on mechanism design, which was the revelation principle, was developed by Professor Maskin himself with Dasgupta and Hammond, Myerson and Harris and Towson. And basically what the revelation principle guarantees is that if you take any equilibrium outcome of any arbitrary mechanism, you can replicate it by an incentive compatible direct mechanism. As it turns, so Professor Maskin made many contributions to mechanism design, but if I want to single out a point where he stands alone is in implementation theory. That is, mechanism design guarantees that there is an equilibrium which implements the optimal location. But there might be very bad equilibrium as well. So think about banks. Banks do this mechanism, a wonderful mechanism for doing material transformation, but they also have like run equilibrium, which is really bad. So in 1977, Professor Maskin wrote a paper that basically defined the concept of Maskin monotonicity, as it became to be known, which if a social choice rules doesn't satisfy this condition, it cannot be implementable. And if it does, and providers like a no veto power, then it can be implemented. So if it were not enough, his contributions to theory directly, Professor Maskin also advised some people. The first person that he advised, I think, if I'm not mistaken, was Jean Tirole, the Nobel Prize winner of 2014. And some other people like Drew Funderburg, still when he was at MIT, and at Harvard, Abhijit Banerjee, Matthias de Watripon, Sandeep Baliga, and some others that we all have heard of. So that it says a lot about his contributions to economics. It goes not only through his direct impact, but everything that he did to form a community of great economists. So it is my pleasure to welcome Professor Maskin.
Thank you very much. That was a lovely introduction, Carlos. And Myrna, thank you for this invitation. It's great to be back in Rio at FGV. I've been here often before, and it feels like home coming back. Unfortunately, I can only be here for a brief time. I'm just here for the day. But I made a point of squeezing this in because I know that this is a celebration for my old friend, Aloisio, old friend and great economist, and I didn't want to miss that occasion. So it's great to have the chance to be part of the celebration. I thought what I would talk about today, rather than talking about mechanism design, although I like that subject too, is some recent work that I've been doing with Jean Tirole on Markov equilibrium. There is a connection with public economics, and I will make that connection in a little while. But first, let me try to set the scene a little bit. What is the idea of a Markov equilibrium? Well, as we know, in dynamic games, in games which take place over time, there can often be lots and lots of equilibria. One of the reasons for focusing on Markov equilibrium in particular is because this enables us to narrow down the set of possibilities. And the basic idea of a Markov equilibrium is that a player's behavior should depend only on those aspects of the past which still matter, which are payoff relevant now and in the future. Let me give an example of what I mean. Suppose that player I's payoff is a weighted sum, a discounted sum of payoffs in period 1, period 2, ... where player I's payoff in period T depends on the actions taken in period T, and I'll denote actions by vector A sub T, but also on the state of the system, ST. So player I's payoff in period T depends on AT and ST, where ST, the state, depends on the actions that players took in the previous period and also on the state that prevailed in the previous period. Well, if we looked at an equilibrium, an unrestricted equilibrium, player I's strategy could in principle depend on everything that has happened in the game up to period T. So that all of the previous actions, all of the previous states. But in fact, if you look at player I's payoff in period t, it's only st, the state in period t, that directly affects player i's payoff that period. All of the other aspects of the past, all of the previous actions, all of the previous states don't matter because they don't enter player i's payoff function in period t. And so, in a sense, the period t state is a sufficient statistic for all that has happened, and a Markov strategy for player I should depend only on the state st. That's the basic idea of a Markov strategy. Now, in the example I just gave, the set of possible states was given exogenously. We just said, suppose that we have a state in period t, state in period t minus 1, and so on. We didn't say where this state space came from. The task that Tirol and I have set ourselves is to try to derive the state space from the underlying game. That's a major feature of our project on Markov equilibrium. And I'll tell you in a few minutes how we have proposed going about deriving this state space. But let me first say a few more words about why we're interested in Markov strategies and Markov equilibrium in the first place. I already mentioned one reason, which is to try to make sharper forecasts about what will happen. But there's, I think, a deeper theoretical reason for being interested in Markov strategies and Markov equilibrium, because there's a clear sense in which Markov behavior is the simplest behavior that is consistent with rationality. If you think that people, given a choice between behaving in a simple way and a complicated way, will, all other things being equal, behave simply, then Markov behavior is a natural kind of behavior to focus on. If, for example, people learn their behavior from experimentation and people use simple experiments before moving on to more complicated experiments, you might expect them to discover Markov behavior from experimentation. So just to emphasize this point again, in Markov strategies are depending on as few variables as possible. Strategies depend only on those variables which still actually matter. So we're ruling out what are called bootstrap equilibria. Bootstrap equilibria are ones where player I conditions on some previous variable x because j does so, and j does this because I does so. In other words, they're making their behavior conditional on some irrelevant variable just because the other player is doing it. If the other player does it, I have to do it too. Markov equilibrium rules that out. It also captures the idea that that what has happened in the past should be forgotten. In English, we have this expression, bygones are bygones. And formally, what this means is that if we have two different games, which from a certain point look the same going forward, then they should be played the same way, even if the histories leading up to those two games are quite different. In other words, the past shouldn't matter as long as the future is the same in two situations. Another reason for being interested in Markov equilibrium, I'm not going to dwell on this point today, but it's in the papers that John and I have written, is the idea that if we change the variables, the past variables a little bit, we should change equilibrium behavior only by a little bit. In other words, Markov equilibria, unlike equilibria in general, have good continuity properties. But maybe the most important practical reason for being interested in Markov equilibrium is what I said before, that it enables us to focus on a clear-cut class of possible predictions. And this is one reason why Markov equilibrium has been important in many applications. It's been important in industrial organization for understanding dynamic oligopoly. It's been important in political economy, and this is the connection with this conference, public economics. In a lot of the literature on, say, dynamic taxation, on dynamic public goods, Markov equilibrium has been the solution concept. It's been important in macroeconomics for understanding monetary policy over time, many, many applications. Okay, so those are the reasons for studying Markov equilibrium. What can I say about our contribution to the subject? Well, I'm going to try to focus mainly on our current work, our recent work, but to build up to that, let me mention a paper that we published now quite a long time ago, 15 years ago, on complete information games. So let's imagine a finite period game, a game that lasts for capital T periods. Player I's payoff depends on the actions that players take in each of those capital T periods. So in period little t, in any period little t, the history of the game is just the sequence of actions that have been taken in previous periods, period 1, period 2, up to period t minus 1. And for the case of complete information, we're going to suppose that the history is common knowledge, so that there's no private information in this setting. One way we can rewrite player I's payoff is as a function of the history, which is ht up to period t, and the future, ft, which is the sequence of actions starting in period t going to the end of the game. So we're basically dividing the actions up into what has happened before and what is going to happen from now on. Now, if we just look at a general strategy without any restriction, player I's behavior in period little t will depend in general on the entire history of the game up to that point. And in order to look at equilibrium, we need to define player I's payoff as a function of players' strategies. So let's define player I's payoff conditional on the history HT having already occurred, given a vector of strategies as player I's expected payoff given that history, given the strategies, where the expectation is taken over all possible futures, all possible future actions that could have been taken given this strategy, sigma. So we're allowing for the possibility of randomness. It may be that these strategies involve some randomization, or it could be that there are random acts by nature. So that's player I's conditional payoff, conditional on history HT. Well, now we can define the standard concept for dynamic games of complete information, namely subgame perfect equilibrium. A subgame perfect equilibrium is just a vector of strategies such that no matter what history HT has occurred, player I is maximizing from that point on, given the strategies of the other players. In other words, player I does at least as well by playing his equilibrium strategy as by playing any other strategy starting in period T. But the idea of Markov equilibrium and Markov strategies is that we don't want strategies to depend on the entire history. We want strategies to be less sensitive to history than subgame perfect equilibrium allows for. We want, in other words, we want a player to play the same way given two different histories which lead to equivalent payoffs in the future. So intuitively, we want player I's strategy to depend only on some partition of history. A partition is a way of dividing up the past into different subsets, where for all of the possible histories in each subset, player I plays the same way. And the coarser is this partition, that is, the bigger the subsets are, the less dependent on the past player I's strategy will be. So that's the idea. So here's how we try to accomplish that. In period T, let's H sub T be some partition of the period T histories. So capital HT of little ht is is a subset. It's a subset of histories which are in the same subset as little ht. And I refer to this idea of coarseness. We want partitions to be as coarse as possible because that makes strategies less dependent on the past. One partition is coarser than another, so H is coarser than H prime if each element, each subset of H prime is a subset of some subset of H, where this is a weak inclusion, but for some value of t and some possible history, this inclusion is strict. And basically, we want to look for the coarsest possible partition, which is consistent with optimizing behavior, which is consistent with rationality. So we'll say that player I's strategy is measurable with respect to a partition if the strategy chooses the same action for all histories in any element of that partition. So if history ht and ht prime are in the same subset, the same element of the partition, then if player I's strategy is measurable with respect to that partition, I will play the same way after ht as after ht prime. We'll say that the partitions are consistent, and here by that I mean consistent with rationality, if whenever the other players are using strategies which are measurable with respect to their partitions, player I does not lose if he makes his strategy measurable with respect to his partition. And the formal way of saying that is that player I's decision problem, or after ht, is equivalent to his decision problem after ht prime. So I use the equivalent sign. I'm not saying that his payoffs are necessarily the same after ht and ht prime, but his von Neumann-Morgenstern preferences are the same after ht and ht prime. In other words, he faces the same decision problem after ht and ht prime, and therefore he doesn't lose if he makes the same decision after ht and after ht prime. So he can, without loss of generality, make his strategy measurable with respect to his partition. Now, one immediate but important lemma for the case of complete information is that if everybody's partition is consistent, then all of the partitions have to be the same. Actually, this isn't true in complete generality, but it's true except for highly degenerate games. And let me explain why it's true. Suppose that history ht and ht prime are indifferent elements of J's partitions. Suppose, furthermore, that the game is sufficiently non-degenerate so that there is a way that J can behave after HT and after HT prime so that player I's decision problem after HT and HT prime is different. So the game is not so simple that player I can always play the same way. J has a way of behaving after HT and HT prime so that I's decision problem is genuinely different for these two histories. Well, then that must mean that if player I's partition is consistent, HT and HT prime must be in different elements of the partition. Player I cannot behave the same way after those two histories. And so what we're saying is that if HT and HT prime are in different elements of J's partition, then they must be in different elements of I's partition as well. And that's the content of this lemma, which is enormously simplifying because it means that from now on we can just look at a single partition. We don't have to look at different partitions for different players. This will change, by the way, once we get to the case of incomplete information, but for now it's the same. So let us look at consistent partitions which are maximally coarse. Maximally coarse means that the elements of the partition are as big as possible. And we'll call a maximally coarse consistent partition a Markov partition. And the first thing we need to establish is that this is a well-defined concept, that there is a unique maximally coarse consistent partition. This is not on its face obvious because there could be multiple. In principle, there could be multiple maximally coarse partitions. But here is a proof that, in fact, we get uniqueness. Suppose we had two maximally coarse consistent partitions. What I can do is to take what is called the finest common coarsening of those two partitions. So one partition is H naught, the other partition is H double naught, and now we're going to create a third partition, which is the finest common coarsening of H naught and H double naught. Let's call that H star. Now, H star is coarser than either H naught or H double naught. So if we can show that it's consistent, that proves that H naught and H double naught were not maximally coarse because H star is even coarser. So the only thing we have to do to complete the proof of uniqueness is to show that H star itself is consistent. Well, here's the proof. Suppose that there are five possible histories, which I've denoted by these dots. So here, 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 and here. And H naught is a partition which divides up the possible histories into two elements. The first element consists of these two histories, and the second element consists of these three histories. H double naught also divides up histories into two partitions, but now the elements are first these three histories, the dividing line for H naught is after the second history. The dividing line for H double naught is after the third history. So the first three histories are in the first element of H double naught, and the remaining two histories are in the second element. So H naught and H double naught are clearly not the same partition. If we try to take the finest common coarsening of these two histories, we get a partition in which all five histories are in the same element. Now we're assuming that H naught and H double naught are consistent. We have to show that H star is consistent. Well, let's focus on two histories, HT, which is the second dot, and HT prime, which is this fifth dot. They're in the same element of H star. They're in different elements of H naught and H double naught, but they're in the same element of H star, and so it better be the case that player I's decision problem after HT is the same as that under HT prime. But that's quite easy to show, because from H double naught, notice that HT and this third history, the history right next to HT, those two histories are in the same element of HT double naught, and so player I's decision problem after this second and third history must be the same, because we're assuming that H double naught is consistent. But the third history and HT prime are in the same element of H naught. And so, once again, player I's decision problem after this history and after HT prime must be the same. And so putting those two statements together, player I's decision problem after HT and HT prime must be the same, showing that H star is consistent after all. And so we have a unique Markov partition, which is what we wanted to show. In the case of complete information, we now have a natural way for any dynamic game of saying what the state space is. The state space is just the Markov partition, and this is a well-defined notion because the Markov partition is always unique. And a Markov perfect equilibrium is now just a subgame perfect equilibrium where strategies are measurable with respect to this unique Markov partition. And you can show that, at least in a finite game, a Markov perfect equilibrium always exists. You can give conditions under which you get existence even for infinite games. There's a continuity property that's involved. The theory is really very nice and very simple. But now let me turn to the focus of the more recent work, which is incomplete information, where you will see that things are a little bit more complicated. So now let's suppose that at time 0, before the actual game begins, each player gets a private signal. So player I gets a signal theta I, which you can think of as player I's type. And there's some probability distribution on the joint types. And the important thing is that player I knows what theta I, the value of theta I is, but the other players don't. And now we'll make player I's payoff depend not only on the actions that players take, but also on their types. So a strategy for player I, in general, will now depend not only on the history of the game up to period T, but also on player I's type. And just as we defined player I's payoff as a function of strategies and histories for the complete information case, we can do so in the incomplete information case. There's no change at all. Everything is the same, except that now we have this additional variable, theta, in the picture, the vector of types. Yes, it's a fixed, well, in the simplest case, it's a fixed type. In extensions, which are not hard to do, you can imagine that types change over time. But for this model, the type is fixed at the beginning of the game. Well, let's try to mimic everything we did for the complete information case. For example, we can now talk about measurability. I'm going to use the term measurable star because this is not quite the same concept we had before, but the idea is that a strategy is measurable star with respect to a particular partition, but also with respect to beliefs about types, if whenever two histories are in the same element of the partition, and whenever beliefs about other players' types are the same after HT and HT prime, then player I takes the same action after HT and HT prime. So the important difference here from before is that we now have this requirement that beliefs be the same. Even if the histories have been the same, even if the histories are in the same element of the partition, if the beliefs are different about other players' types, then player I might want to behave the same in a different way after HT and HT prime. And that's why we need this second requirement, that not only are HT and HT prime in the same element, but the beliefs about other players' types are the same after HT and HT prime.
All realizations of the other players, not only because this is for the whole realization of the other players' type, or is on the path?
So far, we haven't even defined equilibrium. So we're just talking about what it means for a strategy to be measurable. And we haven't said where these beliefs come from. These beliefs could be correct, they could be incorrect. They're just arbitrary beliefs, but we can talk about measurability with respect to those beliefs. And this is what it means. And now we can talk about consistency in the case of incomplete information. A partition will be consistent if whenever players are using strategies which are measurable with respect to their partitions, their decision problems are the same after HT and HT prime when the partition is consistent with respect to the true beliefs. So remember, there's some common prior on types at the beginning of the game, and from that point on, players can update those beliefs using Bayes' rule and the strategies that other players are following. So I don't know your type, but I know the strategy you're following, and so I can update my beliefs about your type based on what you do. Those are the true beliefs, which I'll row bar. We'll say that a partition is consistent with respect to the true beliefs if whenever other players are making their strategies measurable with respect to their partitions, player I can safely do the same. So player I's decision problem is the same after HT and HT prime. So far everything is as analogous to the complete information case as could possibly be expected. This is an obvious generalization. And we can once again define a Markov partition as the maximally coarse consistent partition. Following exactly the same kind of arguments that I went through before, we can show, in fact, that we get a unique Markov partition. It turns out to be a little bit more complicated in the incomplete information case because now different players might have different partitions because they don't, in particular, they don't observe the other player's type, but still, under fairly mild conditions, we get a unique Markov partition. The problem, though, is existence of equilibrium. The natural thing to do in the case of incomplete information is to define a Markov sequential equilibrium as a sequential equilibrium in which players' strategies are measurable with respect to the Markov partition. But even in quite simple games, such an equilibrium may not exist. And let me show you a simple example where there's a serious existence problem. It's a two-period game. There are two players. There's a buyer and there's a seller. And they discount the second period with discount factor delta. The seller has a single indivisible unit of a good for sale, and the seller places no value on this good himself. He just wants to get the maximum possible price for it. The buyer has two possible values, a high value and a low value. And the probability of the high value, theta h, is rho. Probability of the low value is 1 minus rho. So how does the game proceed? Well, in the first period, the seller will offer a price to the buyer, price P1 for period 1, and the buyer can accept or reject. If he accepts, the game is over and they transact at the proposed price. So that means that the seller is going to get P1 and the buyer is going to get his value for the good, theta, minus the price he pays, P1. If the buyer rejects, then we go to the second period, and once again, the seller can make an offer. Now it'll be P2. If the buyer accepts, then they transact at P2. So the seller gets P2 times the discount factor delta, because this is one period later, and the buyer gets theta minus P2 times delta. if the buyer rejects the second offer, then both players get 0, and that's the end of the game. So very simple game. This is a game which probably many of you have seen. It's a sort of textbook example of incomplete information in dynamic games. But let me show you that it has no Markov equilibrium, which is quite interesting. And here's why. Let's suppose that the probability of the high type is high enough so that this inequality is satisfied. So rho theta h is bigger than theta L. This will give the seller the incentive to set a high price rather than a low price, even when he's not sure that the buyer is of a high type. Let's imagine that in the first period, the seller sets a price which is a little bit less than theta h. Now this may not be an equilibrium thing to do. In fact, it won't be part of equilibrium behavior, but for a Markov sequential equilibrium, we have to make sure that for every subgame, or for every continuation game, strategies are optimal, and in particular strategies have this Markov property. So I'll be looking at continuations after P1 has been proposed. Now, in the second period, everybody knows that the seller is either going to choose a price equal to theta h or theta L, because there are only two possible buyer types. The buyer can be high or low. There's no point in setting a price in between. Either the price is going to be high or low. Suppose that in this continuation equilibrium, the price in period 2 is high with probability 1. Well then, a high type in period 1 is going to accept this price, theta h minus epsilon, because he knows that the price is going to be even higher the next period. So a high type will accept P1. But then that means that P2 cannot be theta h, because the seller will know in period 2 that he's facing a low type. The high type will have accepted already in the first period. So the buyer must be of a low type. But that contradicts our assumption that P2 equals theta h. So it cannot be the case that P2 equals theta h with probability 1. And for an exactly symmetric reason, it cannot be the case that P2 equals theta L with probability 1. Because if it equaled P2, if P2 equaled theta L with probability 1, then the high type of buyer would always reject P1, in which case the seller would want to set P2 equal to theta h in the second period, contradicting this assumption. So all of this tells us that in the continuation equilibrium, P2 must be a randomization. The seller must be randomizing between theta h and theta L. Suppose that the probability of theta L is x and the probability of theta h is 1 minus x. Well, that must mean that the seller gets the same expected payoff from setting theta L and theta h. And this is this is the condition of indifference, which says that the seller's expected revenue is the same in both cases, where where rho prime are the seller's updated beliefs about the buyer's type after seeing that P1 was rejected. Now notice that rho prime does not depend on P1. In particular, rho prime does not depend on epsilon. So from the seller's point of view, it shouldn't matter what price he sets in the first period. All that matters in the second period are his beliefs about the buyer's type. And that means in particular that the seller's randomization between theta H and theta L cannot depend on P1. That would be a violation of the Markov principle that your behavior should not depend on irrelevant parts of the past. So X should be independent of P1. But just as the seller must randomize between theta H and theta L to have a well-defined continuation equilibrium, the theta H buyer must also randomize between accepting and rejecting P1, which means that the theta H buyer must satisfy this equation of indifference. This says that the high type of buyer is indifferent between accepting P1 and rejecting P1. This depends on X. This depends on the probability that the seller will set the price equal to theta L in the second period. But notice that this X depends on P1, violating the Markov property. So we proved that there is no Markov sequential equilibrium in this game because in particular the randomization that the seller does in period 2 has to depend in equilibrium on some irrelevant information about period 1, namely what price the seller set in period 1. So there's no Markov sequential equilibrium. What's going wrong here? What is the technical problem that is arising? Here it is. In a Markov sequential equilibrium, a seller's strategy has to be measurable with respect to beliefs. When beliefs change, the strategy changes. But the problem is that even if the game itself is finite, even if there are only finitely many actions, the belief space itself is a continuum. And because beliefs are so important in incomplete information games, there is a natural difficulty, which is that strategies may be discontinuous in beliefs. Equilibrium strategies may be discontinuous in beliefs, meaning that we cannot apply the standard fixed point theorems to guarantee that equilibrium exists. So that's the technical problem that the buyer-seller game illustrates. Well, what do we do about that? One natural way to proceed would be to try to restore continuity by restricting beliefs to a finite set. Now, that ensures that we get a fixed point. The problem is that if we limit the set of beliefs, if we say that beliefs can only lie in this finite set, it could be that in equilibrium the beliefs will be wrong because the true beliefs might not lie in that finite set. But that what we can then do is look at a sequence of grids, of finite grids, which more and more closely approximate the continuum. And we can look for limits of equilibria as the grid goes to the continuum. And that's what we propose. So our definition of an epsilon Markov sequential equilibrium is the same as a Markov sequential equilibrium, except that we now require that beliefs have to be correct only up to epsilon, because we're focusing on this grid. They might be epsilon off, but now we look at a sequence of epsilon equilibria as epsilon goes to 0. Just to illustrate how this would work in the buyer-seller game, there exists an epsilon equilibrium in which after P1 is rejected, the seller either has beliefs slightly above rho prime. Remember, rho prime are the beliefs in which he would want to randomize between the high value and the low value. In this epsilon equilibrium, he might choose, his beliefs might be slightly off, either slightly below rho prime, in which case he wants to set the price equal to theta 2 with probability 1, or his beliefs might be slightly above rho prime, in which case he will want to set the price equal to theta h for sure. And so this uncertainty about the seller's beliefs plays the role of randomization. But notice that we no longer have dependence on irrelevant variables. So this is although there's randomization, it's purely in a Markov kosher way. Well, that's very briefly is our conceptual proposal to define, for games of incomplete information, to weaken Markov equilibrium so that for games like the buyer-seller game, we still have a Markov sequential equilibrium. You might ask, well, does this weaker concept still have cutting power? Does it still fulfill the Markov goal of restricting the set of equilibria? And the answer is yes. You can show that the only role that this weaker concept of Markov equilibrium plays, the only difference between this concept and the standard concept is that now randomizations might depend on irrelevant information about the past, but that the set of variables over which you're randomizing are still Markov. So in other words, the only practical difference between this concept and the stronger concept is that the randomization probabilities themselves might be non-Markov. That still gives us a lot of cutting power, and therefore we are hopeful that this will be a useful practical concept in the applied literature. But that remains to be seen. No, we don't get uniqueness, but we didn't. we don't get uniqueness even in the complete information case either. The Markov partition is unique, but there could be multiple Markov equilibria for that given partition, even with complete information. So you don't get uniqueness, but in general you get a much smaller set of equilibria than you do when you allow for any possible strategy. Yes, so this limit exists. Yes, that always exists. So this is a well-defined concept.
Yeah.
It may not be unique, but we always get an equilibrium. And then the remaining question is, how does this concept of Markov equilibrium differ from the stronger concept, the concept that we started with? And I was suggesting that the differences are not all that important, practically speaking, because they really just involve randomization probabilities. And that's really all I have. So let me thank you for your attention.
Okay, let's thank Eric first. So are there any questions, any comments besides those that we've had already? Okay, I have one actually. Okay, and with regard to my own work, I've heard the comment that, well, epsilon equilibria are not exact, right? I mean, you know, and I think they're exact. Epsilon is greater. How would you answer a concept like this? I mean, or not a question like that? You know, if somebody said, well, this is not exact, you know, any epsilon equilibrium.
It's correct. Epsilon equilibria are not exact. We're not actually taking a position on the foundations of epsilon equilibria in this paper, because in the end, our equilibria are exact.
Well,
in the
yeah,
end, we're taking a limit.
Okay.
The epsilon equilibrium is really a technical device
Right.
for getting around an existence problem. If we drop the epsilon here, there may be no equilibrium,
Right.
and so the epsilon restores equilibrium, but then we make the epsilon go away
Go to zero. So
by
it's taking the limit
epsilon
that you view as
to zero. So in the limits,
yeah.
Beliefs are actually correct. I should say that usually when people do epsilon equilibria, when we talk about the equilibrium refinements literatures, some of you probably have heard of the idea of trembling hand perfect equilibrium, which is a sort of epsilon equilibrium idea. Usually when we look at epsilon equilibria, it's from the point of view of strategies being a little bit off. Strategy sigma is the correct strategy, but players are using sigma prime, which gets them a slightly lower payoff. The interesting contrast here is that in this epsilon equilibrium, the strategies are always perfectly optimizing, but it's the beliefs which are slightly wrong. So we're slightly wrong. Players are slightly wrong about other players' types. So there's an interesting duality between this kind of epsilon equilibrium and the usual kind.
Interesting. Yes.
So I imagine that whenever there is an
You have a
equilibrium. Oh,
microphone,
sorry.
so why not use it?
I imagine when there exists an equilibrium, then the limit of the epsilon equilibrium will be the equilibrium, right?
Yes. Yeah.
Okay.
Well, one of them will be. So there could be others, though.
Okay.
So when that's right. When there is an MSE, a Markov sequential equilibrium in the strong sense, then in particular one possible limits will be this strong equilibrium, but there might be there might be other equilibria because this concept is weaker. The point I'm making, though, that I was trying to make before, though, is although you might get more equilibria, they won't be all that different from the strong Markov equilibrium, because they'll just involve differences in randomizing.
Mm-hmm. Okay, we have
I think-
Raba. Oh, sorry.
I think Aloisio had a question, and
Oh,
since it's his
Aloisio?
birthday, he
Oh, right.
you should get to ask it.
You second.
It's easy to prove the equilibrium, no? Existence of equilibrium in this context. That's not Markov, right?
Right.
Another thing is, in general equilibrium, we have this problem also to find the Markovian equilibrium. No?
Right.
That might be useful in that context also. Have to try to get in these grids and then get the limit.
Yes, I mean, you're right that the literature, the general equilibrium literature has this same
Problem.
has this same problem, and we conjecture, although we haven't tried it, that these same techniques could be useful in general equilibrium.
Yeah, that's
too.
what I'm figuring. That might
Yeah.
be a useful idea in that context also. No?
Right.
I think Raba is next. Raba Amir.
Yeah, so first, thank you for a very nice, very clear presentation. So the counterexample indicated perhaps something that must be completed in the definition of Markov equilibrium when you have incomplete asymmetric information, because the usual framework talks about the property of Markovness with respect to a very natural state variable.
Right.
But there's no formal definition of the concept if you start from a framework where there is a priori no natural state variable. So I'm just wondering whether when you go to incomplete information, whether the debate should not revolve around how to augment the state space in a natural way, such that the sort of equilibria you get here would be Markov with respect to the augmented state variable.
Right. Good question. A fundamental goal of our work is to define what the state space should be, and for the case of complete information, we found that there is an unambiguous definition, a definition which not only accords with the usual ad hoc definition where there's already a state space there, but also gives you all the nice properties of Markov equilibrium and existence that you would want. In the case of incomplete information, you can still define the concept of a Markov strategy and a Markov partition in an unambiguous way. You get uniqueness again of the Markov partition, but then there's this equilibrium existence problem. And you're right that an alternative way of patching up the problem would be to expand the Markov space, the state space, to allow strategies to depend on a bit more than just payoff relevant variables. So for example, in this in this buyer-seller game, what we could do is to introduce an additional random variable and if the random variable comes up high, then the seller sets the high price, and if the random variable comes up low, then the seller sets the low price in the second period. And that takes care of the Markov property, because now strategies are depending only on the on the states. Yes, we could do it that way. The problem is that there's no guarantee when we do it that way that we're adding the minimal. What we want to do is, if we have to add other variables, we want to add as few of them as possible, and while still getting the Markov property. But by doing it our way, we're sure that any additional non-Markov properties are as small as possible. If we did it this alternative way, where we expanded the state space, there's no obvious way, at least not obvious to me, how we would make sure that we're not adding more than necessary. But in principle, you're absolutely right that is a valid way to go.
Okay, I think unless anybody has a pressing question, we should adjourn for now, and let's thank Eric again for this marvelous lecture.
Okay.